Okay, hello guys. So I'm sorry. I think I got some inconvenient, and I think we can start now. Let me check. Yeah, now it's working. Okay, guys. So let me share my screen. Okay. So I'm gonna, uh, I don't want you to see my ceiling. I'm gonna put my computer down. So I'm gonna start my camera. So here in the okay, we can start now. So I was saying that we're gonna talk about today Taylor series. Uh, we're gonna talk about what how can we define uh, a, a function in general uh, as or how can we see a function as a power series. So today is probably one of the most important theorems of the whole calculus. Okay, so you have a power series. We already saw this. So this is the kind of series we define. That's what we call a power series, right? And so the example let's think about it. So we want to talk about what kind of, if this is a function. This is, we have been saying, uh, these are functions if they pass the ratio test, okay, for some in some interval, okay. So the question we have to answer is, how powerful is this? So can we write a series for the exponential function? Can we write a series for sine of x? Can we find a series for cosine of x? And the answer for all this is yes. Each of these functions is going to have a power series, okay? So any good function that we have seen you have seen until today, sine hyperbolic, cosine hyperbolic, uh, is gonna have a representation as a power series, okay? And sometimes it has to be on interval, on a small interval, but still is gonna be good enough when you are because you want to represent it. So before going here, we need to, so we already say exponential. We already have been working with this one. We said this was 1 plus x squared over 2 factorial plus s cubed over 3 factorial plus x to the 4 over 4 factorial, and so on. And this theory is so beautiful that you are going to understand why the series looks like this, okay? And then we have been having a hard time finding this radius. So in the power, when we go back to see power series, we have been finding all these limits. And for example, we did the Bessel function. Okay, so we have the Bessel function, and this is defined over here. It's a very weird function, but we already saw that this function helps you to model vibration of a drum, like a very mechanical situation, right? And this J series associated with the frequency, okay? So we're in front of a really important method, but remember we were saying, is this a function? And what we did was the ratio test to figure out where is this a function. And when we did the ratio test, we found that it's good for any x. So this function is a beautiful function. This function is as good at exponential, at sine of x, at cosine of x, because this function is differentiable. It's going to be differentiable, and you can also integrate this function. Okay? So this function is all that you want. And it doesn't look like anything you had seen before. Okay? So what we're going to do today is give some context. Okay? So another function we have been working on, or another example was this. We had one, which is my color, 1 plus x squared plus s cubed plus x to the 4, and so on. So if somebody remember what is this? This function looks like what? This series. This series looks like what? We had talked about this before. What does it look to you?
Sequences.
Don't remind you anything? So what about this? We got put 1 plus 1/2 plus 1/2 squared plus 1/2 cube plus 1/2 to the 4,
A sequencer.
and so on. What is this? What is this one? What is this series? Yeah, somebody's telling me geometric. Yeah, that's the geometric. Who's that? Francisco. Francisco Patiño. Yeah. So this is it's a geometric series, right? And what is the sum? What is the sum of this? 1 plus 1/2 plus 1/2 squared and so on. What was the final sum of that? You guys remember? Infinity, no. So Rene is telling me infinity, no. Yeah, 1 over 1 minus r. That's correct. So this is 1 over 1 minus 1 over half. And what is that? Because when we're doing geometric, r is 1/2. And if r is between 0 and 1, then that's the formula we have. Okay? So here, if your x, if the absolute value, so it could be also negative, if the absolute value of x is less than 1, okay, this sum will be 1 over 1 minus x. Okay, so that tells you, that gives you another example. This time we know where it is coming from. This is a whole series. So all this looks very nice, but it's infinity. It's an infinite sum. So it looks like a philosophy problem. Okay, but when you can tell me this infinite sum is 1 over 1 minus x, then that's something extraordinary, because it's an infinite process, and still you can give me a number. So the same that here, all this infinite sum is gonna give me a 1 minus 1/2 is 1/2, so this sum is 2. So all this sum is equals to 2. All the sum at the top is 1 over 1 minus x. So we are gonna write similar thing, because for example, if I give you, what is the power of this? So for example, if instead of x, I say e to the 2, okay? So if I write e to the 2, so let me change this x for 2. So if I change x for 2 everywhere, so that will be 2. Let me erase all this. 2 squared, 2 cubed, 2 to the 4. all that, this infinite sum over here is gonna give me e to the 2. Okay, so that's the power of this. This infinite sums is gonna give me a number. So far, until pre-calculus, you only know something like the ratio test over here. Oops. Okay, like this. Now you're gonna be able to give me so many infinite sums. Okay, for one application. Okay, but we have much more interesting than that. So as I told you, we already have the Bessel function that is used in a real physics application. And if this is a function, for example, if this is a function now, right? If this is a function, can we find the derivative, right? If this is a function, obviously I can find the derivative and the integral of the right-hand side. So what is the derivative and the integral of the left-hand side? So basically what question I'm trying to make is, what is the derivative of Cn x minus a to the n? What is the derivative of a series? And what is the integral of a series? N equals 0 to infinity, n equals 0 to infinity. Okay? So, and since you are engineers, you have a good intuition for this. So I'm going to ask you, so if f of x, let me give you just something like this, sum of x to the n over n factorial, n equals 0 to infinity. What do you think will be f prime of x? A naive guess, an ignorant guess. But at the end, it might be a good guess. So if you have this infinite sum, what do you think could be the derivative? If this is 1 plus x squared divided by 2 factorial. Well, let me forget about the factorial. Just put 2. So you focus on the important. X to the 3 over 6 and so on. Somebody wants to give me a guess? What will be the derivative of that? What will be the derivative of this series? What do you think? Somebody has to talk. You guys are not talking today very much. You can make a guess. Otherwise, it's not fun.
Is it 1, sir? Like a constant or no? Hello, sir?
So if the derivative, let's see, what is the derivative of 1? Let's take the derivative of 1. What
Would
is
it be
it?
the same thing?
The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared divided by 2. Oh, somebody said that it's trying to talk, but I cannot hear them. Let's see, Rene. Oh, you okay? It's more people is saying that you cannot hear me. Yeah, sorry guys, I cannot hear you. Let's see. Let me see something weird. Okay, now I can hear somebody. Can you say something?
Hello?
Say something, please. Who's that?
Hello?
Hi.
Yes. Who are you?
Do you hear me, sir?
Yes. Who are you, please?
I'm Rene.
Rene. Okay. So now I can hear you. Were you trying to say something and I couldn't hear you or not?
I was trying to say something, but it's okay.
Okay. Okay. So yeah. So maybe you had to unmute yourself, guys. Maybe you are mute immediately, so you had to unmute. Okay. So what is the derivative of one is zero? The derivative of x is one. What is the derivative of x squared divided by two?
X.
Will be x. And the derivative of s cubed divided by 6. That will be,
X
X
over
squared
2.
over 2.
yeah, 3x squared over 6. That is s squared divided by 2. So you see, if I'm not saying this is a process you can keep going because it's infinity, it's an infinite process, right? But maybe it makes sense to find the derivative of each term because look at what I'm getting. I'm getting s cubed, I'm getting s squared divided by 2, and I get, this is 0, so I forget about, so I'm getting exactly the same series. And I know this guy, you guys remember what is this function? This is the series for exponential function. So this is the series for exponential function. You don't know why, but I told you before. And when I find the derivatives term by term, I getting exactly the same. Look at this. So maybe my derivative is exactly the same as it has to be. So maybe this is the right process to find a derivative. So maybe the derivative of the series is just the derivative term by term of the series. Okay? And that's how beautiful it is. So easy. But you have to be inside of the radius of convergence. So as long the ratio test tells you, let's say you are between minus 1 and 1, then you can just interchange the derivative with the sum. You can interchange the sum with the integral. Okay, so let me give you this before giving you the theorem. Let me give you another one. So another example, since it's exponential function, so I know the integral of the sum x and, well, let me put it just like this. Let me put it like 1 plus x plus s squared divided by 2 plus s cubed divided by 6 and so on. Okay, so you are finding the integral of this series. So maybe you could say, well, okay, well, the only natural thing I can imagine to do is find the integral of each term one by one. Okay, so you'll get what is the integral of 1?
X.
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 And what is the integral of x?
X squared over 2.
X squared over 2. And then the integral of x squared, the integral of this one. What is the integral of this one?
X cubed over 6.
S cubed over 6. So somehow I'm getting my exponential back, right? So the only thing is that I don't have this 1, right? But well, we'll see what is happening. But so so uh, so that is the next theorem I'm going to show you. Okay, so basically, how do you find the derivative of a power series? Term by term. How do you find the integral of a power series? Term by term, as long you are inside of the radius of convergence. So let me give you the theorem, so you have an idea of what is going on. So how we, and then we can move to Taylor. That is really what we're gonna do. And I'm gonna put it here. So this is the theorem. Let me put in red the theorem. And again, this was the kind of physics Russians were really good in the 70s. And why was these people so good and they get so much advantage? You know, they start doing real. I don't remember what was the dog, Laika, or what was the name of the dog that they fly around the air for the first time?
Sputnik.
No, Sputnik was the satellite. I think it was Laika.
Laika, I think it was Laika. Yeah, I mean she died, poor her. But they put the first beam. They fly around, and I think when that happened, that's the United States just said, "Geez, we're losing this." Okay, so this is the kind of mathematics will take you to the moon. So let me write this theorem. So if the power of series sum Cn x minus a to the n has a radius of convergence, r bigger than 0. So remember, that is given by the ratio test. Then the function, so look at this is a function now. Then the function defined by, so as long as you are inside of your radius of convergence, this is a function. F of x equals C0 plus C1 x minus a plus C2 x minus a squared, and so on, right? So in general, this is a function. Inside of the radius convergence, I can call this a function without even worry about it. If I'm not inside of the radius of convergence, this could be anything. This could be just nothing. Everything could be infinity. So I need to make sure I'm clarifying I need inside of my radius of convergence to be a function. Okay. So this is differentiable. On the interval a minus r, a plus r. And the derivative is what we said. F prime of x is just the derivative of the term by term. The derivative of C0 is 0, right? What is the derivative of this guy? What do you guys say? What is the derivative of C1 times x minus a? So you can write it like C1 times x minus C1a. So what is the derivative of that? What is the derivative of C1a? That's 0.
1.
No,
0.
that's 0 because it's a constant, right? And
Yeah.
what is the derivative of C1x?
X.
Actually C1, okay? So what is the derivative of phi x? So you put 1, so you get the derivative of this is 5,
5. Yeah.
right? So don't be, so the C and the A are constants. You just care really about the X. So the derivative of this is just gonna be C1 and then plus the derivative of the next one. The derivative of the next one will be 2c2 x minus a, right? And that's pretty much it. So what the derivative of the next one will be, so basically you just put down the power, okay? Plus 3c3 x minus a squared. By chain rule, x doesn't have anything on the top, in front. So you're done. So the next one here is c cubed x minus a cubed. So that is this derivative. And so on. So just find the derivative term by term. So it's more difficult to do it in general than just do it case by case. So that's the derivative. Now the integral. Okay, and that's something important we were missing. The integral of f of x dx, because is an antiderivative, no? So is c, and it's not a defined, it's not a well defined, like, you know, a and b, right? It's not something like that. When I do the integral of something like that, I need to put the constant. That will be c plus c0 x minus a plus c1. So I'm finding the, well, okay, let me put, yeah, let me put here my f of x. So f of x is c0 plus c1 x minus a plus c2 x minus a squared, and so on. So so my antiderivative is gonna be c0 times x minus 1, c1 x minus 8 becomes plus c1 x minus a squared divided by 2. And then plus c2 x minus a cube divided by 3, and so on. So my point here is that over here we were doing exponential, and what we forgot here was the original constant. So this is all, and this is equals the constant plus whatever we were doing, okay? Because this was not a defined integral. We don't have a and b. Since we don't have a and b, we need to put a constant. And turns out that this constant is gonna be 1. But we will have to figure out, the constant we'll have to figure out somehow, okay? So the whole point here is, yes, you can find given a power series, you can define, you can find the derivative and you can find the integral. And this is extraordinarily useful in real science, okay? So with that, we can move to probably the most exciting part. And, you know, before telling you where is the formula coming from, let me just give you the formula. And so you feel proud of yourself, okay? So how to find this Taylor series of anything. And this, by sure, is gonna be one problem in your exam, in the third exam and in the partial exam. So this is what I'm gonna tell you. Theorem. So this is, you can call it Taylor series of of the function f at a. The function f at a. So if f let me see, how can I write this probably better? Yeah, okay, so yeah, then we can set it out like this. If f of x, let me put that f of x so it doesn't look like an f. If f of x has a power series representation at around a, that
Yo
is
entiendo todo mi programa.
that is if f of x is the sum of n equals 0 to infinity cn times x minus a to the n, and x minus a is less than r, so that's the radius of convergence, right? Then its coefficients are given by the formula Cn equals, this is called the n derivative evaluated at a over n factorial. Okay, so let's, and you're gonna see why is this true. Okay. Oh, you're gonna see why is this true. So this is not only a great theorem because it can be used extraordinary in many applications, but also it's easy to see where is this weird formula coming from. So it's extraordinary. So again, this is probably the most important theorem of calculus that you have seen till now. So only on calculus 3 you will see the other really important theorems is divergence theorem and Green's theorem, and is this related to physics and electromagnetism and mechanical fluids. So this is only those theorems could compare to this theorem. Okay. So again, so let's do an example finally. Okay, example. And I'm going to teach you how to do it in the practical sense, okay? So find the Taylor series of the function e to the x and its radius of convergence. Okay, so basically you have the formula. This is how it goes. You have the formula to find your series, your expansion series. It might work, it might not work. Why it doesn't work? Once you find your formula, you need to find the limit, the ratio test. Once you apply the ratio test, you know the radius of convergence. Because you might have an expansion, but if you don't have radius of convergence, you are not doing anything because that's infinity. Okay, so that's no representation. So first you said, okay, I'm gonna use my formula. So what is my Taylor theorem saying? Really, what my Taylor theorem is saying is this. So pay attention to this. This is the practical way to do this. Sum and then Fn. And okay, I need to tell you what is A. So when A equals 0. So when you are around 0, when A is 0, you call it also Maclaurin series. Okay. So over here, you see in my theorem, A is over here. Right? So if A is 0, it's just gonna look easier for the first example. Okay. And then I evaluate at A. But since A is 0, I just need to evaluate at 0. So I need to find my formula. My formula is f of n. Let me put A divided by n factorial x minus a to the n equals 0 to infinity. That's your Taylor series. Okay. So what you need to do? So you said, okay, a equals 0. And what is f of x? F of x is, what is f of x, guys?
E to the x.
E to the x. Thank you. So what you do next? Well, you see, very easy. So you find f prime of x. What is f prime of x? E to the x.
E to the x.
Second prime of x. What is it? Second
E
derivative.
to the x.
E to the x. Third derivative. E to the x, right? And so on, right? But you don't need this. You need f evaluated at a. In this case, you need evaluated at 0. So f of 0 is 1.
1.
So this is f prime of 0 is 1. The next one is second prime. The evaluated one is 1. Then third derivative, 1. So for all these guys, those guys are 1. So, that's what is my first example. And then you don't want to keep doing lines like that. So you just said f parenthesis 4 derivative. X is e to the x evaluated f4 0 and then gives you 1. So you can keep doing, so you know how the derivative is gonna go. So it's just ones. So really, this guy is son n equals 0 to infinity, f of n 0. So all those guys is just 1 over n factorial. A is 0, so it gets x to the n. So my geometric series is x to the n. But really, this is my candidate. Okay, candidate. Since we're just talking about elections, no? Candidate. You are how do you know this is really the representation? Because you had to tell me the radius of convergence. Okay. Basically, you have to tell me how many votes you have at each state. Okay. So this is the similar. You are a candidate, but you need to show me the ratio test. Without ratio test, you are not the representation. Okay. So we got here. So what is A sub n? So let's use the ratio test. Bn plus 1 over Bn, n goes to infinity. So what is Bn? What is Bn, guys?
X to the n factorial.
X to the n factorial, correct. Thank you. So we can find the limit. So I have to be honest with you. I only understood this really when I was in graduate school. And when I was doing complex analysis, and then we were applying this kind of stuff to physics. Before, for me, it was just limits and things, but I didn't understand the power of this. So bn plus one, what is going to be bn plus one? Let me put it here. Bn plus one is going to be what?
X to the n plus 1 over n plus 1 factorial.
Correct. So I have x to the n plus 1 over n plus 1 factorial divided by x to the n factorial. Okay. So now with this multiply here and this multiply here. Okay. And absolute value, right? So absolute value. Okay, so we go limit n goes to infinity. Then this will go x n plus 1 and absolute value, right? Times n factorial divided by x to the n n plus 1 factorial, right? Now we simplify this, right? We simplify. When I simplify the x, what do I get?
X.
The x on the top, right?
Mhm.
And then n factorial divided by n plus 1 factorial, what do I get there?
1 over n
1.
plus 1.
Yeah, so n plus 1 on the bottom, right? So then what can I do to find this limit?
Take the x
Take
out.
the x out.
Correct. X out. And what is this limit then? What is that limit?
0.
0. So this is really important. X times 0. So for any x, this is 0. This limit, this is 0. So this is less than infinity. So the radius of convergence is infinity. So basically, this series is convergent from minus infinity to, well, I can put it just like the theorem says. Maybe it was you like, what is that? You see, was saying. It was here. It was saying theorem. Where did I roll it? Oh, over here. So this is the a minus r, a plus r. So my radial convergence is infinity. So this is from minus infinity to infinity. So this is going, if you want, you can write it like the theorem is saying. So this is will be 0 minus r, 0 plus r, because a equals 0, right? So, but r is infinity, so really this is minus infinity to infinity. Okay? So this series is totally exponential function. Okay? So this guy is as good as this guy. So it's like when you are saying 1/2. What do you prefer, 1/2 or 2/4? Or you want 4/8? What do you want? Whatever, because it's the same, right? It's 1/2. So it's something like that. These are the same representation. These guys are the same. They represent the same, but they are different. So they have different properties. Okay. So what? In what sense? The 1/2, you read in half of the of the chocolate, right? 2 fourths, you divide it by 4, 1, 2, 3, 4, but you're still eating the same. Oh, I make an extra one, sorry. But they're different, right? They're different because this guy was cut in fourths, this guy was cut in half. So in mathematically, they are kind of different. The same here. This guy is exponential function, this is a series. But in mathematical purposes, they're just exactly the same thing. Okay? So as mathematicians, mathematicians things like that, and that's a useful way to do. Okay, guys. So if I could, I cannot, but this is the time I will make you a fast quiz, and at the end I will give points to the 10 people that finish first. Okay, but we are not under those conditions. So what you're gonna do in this example, please work it out. Example, I'm gonna give you 10 minutes, and then we do it together. So find. I'm gonna use the language because that's what people uses in the books and in Webwork. Find the McLaurin series. So McLaurin series is just Taylor with x equals a. Okay. Sorry, a equals 0. This is McLaurin. Okay. Find the McLaurin series for sine of x. And prove that it represents sine of x for all x. Okay. So please do it. So this, you really need to understand the importance of this. Okay. So sometimes you just take these classes and so many things, you don't know what is important. This is important. From calculus 1, from calculus 2, this is probably the most important thing you have ever seen. And it only can be overcome for calculus 3, that is the divergence theorem and the Green theorem. And sadly, many people, many faculty don't cover this material. For some reason, they skip it. Maybe for time limits or whatever. But we cannot skip this. This is the best. Also, calculus 3. Calculus 3 people last week they do convergence and divergence theorem in one day, and this is the worst, the best thing. Okay, so this is like going to Paris and have a connection in Paris and don't get out of the airport. You need to get out of the airport. This is the important thing here. Okay, so go ahead, do it. I'll give you 10 minutes. Okay, so let's do it together since I only have 8 minutes left. So it's really not that complicated. This is so powerful that becomes easy. So what I want to is represent sine of x as a series, sun, Cn, and is a Maclaurin series. So I want to represent it around 0. So a equals 0. I can say a equals 0. This is go from n equals 0 to infinity. Okay, so that's the representation I want. So I need to find my Cn's. So I need to find first of all, so f of x is sine of x, right? So I need to find f prime of x. So what is f prime of x?
Cosine.
Cosine of x. Then second prime is
Negative sign.
sine. Then I get a third derivative.
Negative cosine.
Sine, cosine, yeah, negative cosine. And let's fourth derivative.
Sine.
Sine, yeah, okay. Let me erase here. Okay, so now we move to the right hand side and we say we need to find at 0. F of 0 is gonna be sine of
0.
0. F prime of 0 is
1.
1. And second prime of 0 is
0.
0. Third prime is
Negative 1.
negative 1. Then the fourth is
0.
4 is 0. So that's 0. And so on. Okay. So let's write it down. Okay. So this will be good enough to get credit. So you can write sine of x equals, well, let me put it like this. See, this is useful. Okay. Do all this. Because, I see it and I see, okay, this person knows what he's doing. Okay, so C0, C1x plus C2x squared over 2 factorial. Oh, no, sorry, no, 3 factorial. C3s cubed plus son, right? Okay, no, I need, let's do C4. C4 x to the 4. And so on. So C0 is f of 0, right? So this guy is 0. Plus C1 of x, so I got x. C2 is 0. So the next one is minus s cubed, right? Oh, sorry, I'm making another mistake now. Sorry, so to avoid mistakes, let's put the whole thing like the real thing, okay? So C0 is f of 0. C1 is f prime of 1, f prime of 0 divided by 1 x. C2 is second derivative of 0 divided by 2 factorial squared plus C3 third derivative of 0 over 3 factorial s cubed, and then plus 4 derivative at 0 over 4 factorial x to the 4, and so on. Okay, so that's probably the best thing you can do. Write it like that, you won't make mistakes. Okay, so again, f of 0 is 0, so I got this guy 0. Now f prime of 0 we said is 1, I got x plus the next one is second derivative of 0 is 0. So this one is gone. So this guy is 0. This one is 0. So I get the next one is third derivative. Is minus. So it's minus x cubed. The next one is 0, right? So what will be the next one?
0.
Oh, sorry, 3 factorial here. Yeah. The next one will be 0. And the next one? Plus,
0. Oh.
yeah, but the next one after that, x to the, what is the pattern basically I'm asking you? X to the,
The n.
X to
no,
Or,
the
no, to
To 5.
5 divided by
5
5
factorial.
factorial.
5 factorial. Then the next one is
X to the 6 over 6 factorial.
but times 0, right? That one is 0. Because we're only getting the odd numbers, right? So what is the next one?
Minus x to 7.
7 over
7 factorial.
7 factorial. So next one is 0, and so the next one is x to the
9.
9 over 9 factorial, and so on. So I just want to see the pattern, right? So basically, are the odd numbers, right? And the sign is changing. So how can we write this? So we can write it like this. Many different ways to write it, okay? So this will be one way. Sum x to the, how do you write an odd number? So you can write it like this. 2 to the n plus 1 over 2n plus 1 factorial. So starting at n equals 0. Because when n equals 0, you will get 2 times 0 is 0 plus 1 is x to the 1 divided by 1. The next one will be 1. That will be 2 times 1 is 2 plus 1 is 3, x cubed divided by 3 factorial, and so on. So now, but we need to now take care of the minus. The first minus is when n is 0, I got 1. So when I get n equals 1, I got minus. When I get a square, so this should be, when it's to the fifth, I'm gonna get, is this right or no? Minus 5.
No.
X to the 5th. No, is I had to fix it. So minus 1. Let me see. Maybe the best thing we can do, this is going 1. Yeah, okay. So it goes with n. The next one will be 1. The next one will be okay. So let's look at this. So this is 1. I don't know. Well, no, actually this is 0. In my counting, this is 0. Then this is number 1. So in number 1, I need negative. This is number 2. I need positive. Oh yeah, so it's good. Because this, I'm counting using this one, right? So this is my 0, n equals 0. This is n equals 1. This is n equals 2. So when n equals 2 is 2 times 2, 4 plus 1 is x to the 5 minus 1 to the 2 is positive. Okay, so this is good. So this is this is my potential, this is my candidate for sine of x. So that's why you practice so much with your homework, trying to figure out those, how to write a series in these terms, okay? Because if you cannot write it like this, you cannot find the ratio test. So we need to find the ratio test for this guy. I know most of you like this one better, right? But we saw that the Bessel function cannot be represented by a normal function. So we need to get more familiar with this dimension. Okay, so now let's do the limit. So I need to find my ratio test to know when is this series convergent, and if it's ever convergent, could be that it's not convergent for any x. So we need to go limit n goes to infinity, bn plus 1 over bn, right? And then I'm gonna do, so this is my a sub n, no? This is my a sub n. So I'm gonna kind of do it because we are for time purposes. So we're gonna do Bn is this guy over here, right? Bn, sorry, no an, but I'm saying Bn so don't get confused with my ans, with my a. Bn is minus 1 to the n x to the 2n plus 1 divided by 2n plus 1 factorial. And the next one, and the third one will be minus the next one will be minus 1 n plus 1, then x to the 2n plus 1. So that will be 2n plus 2 plus 1. Okay, because I have 2 times n plus 1 plus 1. So that's really 2n plus 2 plus 1. So that's really 2n plus 3. So this is really 2n plus 3. So let me just write it down. 2n plus 3, right? Let me know if I make any mistake. So when we do it fast, it's also easy to make mistakes. So that will be 2n plus 3 factorial on the top. Now, we make the eating multiplication, call it like that. And then the minus is gone. We don't worry about the minus because that's why we have the absolute value. Otherwise, this limit will be really hard to find. So thanks to the absolute value, the minus gone. So I'll get x to the 2n plus 3 times 2n plus 1 factorial, right? Divided by x to the 2n plus 1 times 2n plus 3 factorial. Okay? We also have practiced this a lot. So that's what it pays back. So x to the 2n plus 3, x to the n plus 2n plus, okay. Now I can proceed to simplify. Well, actually, I could write 3 like 1 plus 2, right? So I could put it like 1 plus 2. So therefore, x to the 2n plus 1 with this x to the n plus 1, they cancel. And I have limit n goes to infinity x squared. And then 2n plus 1 factorial divided by 2n plus 3 factorial. But what is 2n plus 3 factorial? 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. It's like saying 5 factorial is equals to 5 times 4 times 3 factorial. Okay, this is an easy observation. So I can simplify these guys. Now I proceed to take my x out. I take my x out times the limit. And I get 1 over 2n plus 3 times 2n plus 2. So what do you guys say? What is this limit? What is the limit?
0.
0. For any x, I get s squared times 0. For any x, this is equals to 0. This is less than 1. So this series is the perfect series for sine of x. Okay? Is the perfect series for sine of x and is convergent from minus infinity to infinity. So this is a perfect representation for x from minus infinity to infinity. So this is perfect. For minus infinity and infinity. But I'm not done, right? Because thanks to this, I can find my series for cosine of x. Okay? What is the relation between sine of x and cosine of x? Cosine of x is the, and sine of x are related by the derivative, right? So sine of x, the derivative of sine of x is cosine of x. So I need to find the derivative of that. So if I take the derivative both sides, so let me do it here. So the derivative of sine of x, the derivative of sine of x is cosine of x. Now the derivative of this guy, following what we learned, you just find the derivative term by term. Look at how easy it is. It's gonna take me 30 seconds. Okay, I just need to write the derivative of this guy. Let me make it smaller. So the derivative of this guy, I just need to go term by term. So sum of n equals 0 to infinity minus 1 to the n. What is the derivative of x to the 2n plus 1? It's just 2n plus 1 x to the 2n plus 1 minus 1, right? Just doing term by term. Plus 1 minus 1. Divided by, don't worry, I finished already. 2n plus 1 factorial. So this guy cancel, these two cancel. Look at this. I also have a meeting, so I also have to go. This cancel. And this guy, 2n plus factorial with 2n plus factorial, give me this, the following. Sum n equals 0 to infinity minus 1 to the n. This cancel with this guy, and I get x to the 2n divided by 2n factorial. And this is cosine of x. I'm checking the book. Okay, so in advance, we found sine of x and cosine of x expansion series. And this is good from minus infinity to infinity. Okay, guys, so I'll let you go. So I took a little bit longer because I give you some time to process the example. But so this video is going to be available in course materials. Okay. Okay, guys. So you have questions, you can stay and ask me questions.
All right,
Thank you, sir. Good day.
Okay, thank you, guys.
Excuse me, sir.
Yes.
When is the quiz due?
Oh, I think I put. I don't remember.
Yeah, I tried finding, I saw an announcement, but you didn't specify on the date, and I see it on our course materials, but there's no date either. So I just wanted to make sure when the due date was.
It's probably today or yesterday, because because usually it's for Fridays, right? Or Monday, or for Mondays. But get some extra time. Let me tell you right now.
Okay.
Course materials. Course materials. Sorry. The 13th.
Okay.
Wait, let me check. Yeah, tomorrow. Okay?
Okay, sir. Thank you.
Bye, thank you. Okay, guys, so I'm gonna stop the meeting.
Sir,
Yes?
I have a question.
Uh-huh.
Could you give more day for the Power Series homework?
More time?
Yeah,
Okay, I will give you more time.
the Power Series homework. Yeah.
Okay,
Please. Okay. Thank you, sir.
okay. Bye.
See you tomorrow. Bye.
Okay, see you tomorrow.
Bye, sir. Thank you.
Bye.
Sir,
Yes?
are you gonna have office hours soon, like today or tomorrow?
At 4:30, yes. At 4:30.
Okay, appreciate it.
I had to run for a meeting at 3:30.
Oh, okay.
But at 4:30, I will be there.
All right, cool.
Okay.